And out of interest, how many people were here for my 15-minute lightning talk that went for 45 minutes?
It was too short, isn't it?
Well, those people already know that my organisation style is not organised even vaguely at all, as will be very demonstrable as I do this, which has its pluses and it also has its minuses. Minuses, of course, are just the usual thing of being disorganised, but the pluses are I am quite happy to take questions at any stage, to run off on random topics that interest you. If you go, hey, how about this, sideline about that thing, because basically I know my topic and that's what we're going to be talking about. That's the reason I like whiteboards. You don't have to go by slides and orders. You can just sort of go, here, we'll talk about this. And the other thing is that there are a couple of people here, I think, who are non-programmers. Today is probably, I suspect, going to be one of the more technical sessions that we've had for the game tech group in a while. There have been some fairly technical ones, I think, particularly something like Tom's, for instance. So just for reference, that just because this one might go over your head a little doesn't mean don't come to more game tech meetups, because this one is, as I say, probably going to be a bit more hardcore than some of those. But it is also stuff that I don't think is beyond people who are in the periphery of games and who aren't necessarily programmers themselves. This is stuff I think that is useful for anyone to know. Right, so we'll just dive in. Because we've only sort of got less than 50% who actually came to the first one, we'll do a bit of a recap of what we went through in the first one as well. And again, if you guys have any questions as we go, just shoot. So I might actually even start with the whiteboard. The gist of what I want to do today is basically talk about memory architecture, obviously, but also just the way that a good understanding of memory architecture can actually really change the way you program and design systems for games in general. And that even goes beyond games, really. It is about programming in general, but it particularly applies to games simply because games have I suppose, a particular approach that they both want to be very high performance and they want to deal with a lot of data, basically, structured data in various arrangements and guises. And really what I want to do is, in a sense, break down try and look at the mental model that programmers generally have of the way computers and computer memory works. And I know a lot of you guys already know this, but it's really just for us to sort of deconstruct it a bit. And sort of basically change the mental model people have of the way memory works and the structure and the way you structure your programs around that. And I think a lot of where this comes from is the C language itself, and particularly the C runtimes and the way they operate. So if thankfully this whiteboard has a nice big grid on it, so we can sort of use the grid a bit. The way the C language kind of encourages you to think about memory in a sense is basically you have a pointer which gives you an address in memory, and you, in a sense, you start from 0 and you just have bytes, and your bytes just keep on going to infinity or however much memory you've got. And this is sort of the way that the language in general wants you to think about it, because particularly when you get to C++ and you start dealing with classes, you start basically packing bits of data one after the other, and this is basically the object-oriented approach of C++, and you just sort of keep on adding to these structures, and then you have lots of these structures in memory, and you have pointers to them all so that you know where they fit. And one of the things is that model is a nice, convenient way to structure stuff, to think about it. But when you really start boiling down to the way computers work, and particularly the way they work these days, because of the restrictions on the way that modern computers work, just with the way computers have evolved since the 70s, when a lot of these languages were kind of, in the 60s and 70s when these languages were invented, there are sort of better ways to structure your approach to data. And we are, and I don't know, a lot of these come into, if anyone's heard of data-oriented design, we're sort of almost going to get a bit into that. And data-oriented design is basically an approach to designing your programs around data and data flow as opposed to object-oriented. Now, it's not entirely orthogonal to object-oriented. And for anyone who doesn't know what orthogonal means, that doesn't mean like it's not the two aren't mutually exclusive. You can be object-oriented and data-oriented, but it's a different kind of base way to start approaching how your program works. A lot of what hopefully this stuff should do is give you a grounding so that when you come to, if you've ever found yourself approaching a program and asked yourself, you know, is it worth packing this data tighter, or should I not bother, or should this be an ISA or should this be a HASA for anyone who understands, for people who understand that paradigm as well. It's these kind of questions that hopefully a better understanding of memory models will sort of give people. Okay, so we'll start out. I've got, let's see, actually I'll use some of my stolen visual aids. Great, you know, bad artists plagiarize, great artists steal. So, of course, I haven't made a single image for this entire process. I've actually just ripped all mine off the internet. So I showed this one last time. This is just a random image I found that kind of demonstrates the way you can sort of think about memory. Often we just sort of think about memory in general, but we all know that there's basically a latency relationship in the different parts of memory. It's easy for us, because they aren't explicitly dealt with, to just kind of forget about cache. But cache really is critical not only to the performance of modern applications and software, but also to the way communication between different cores on multi-core CPUs work. And with modern chips, you know, we're easily getting up to 8 cores, and give it another 5 years, I'm sure we'll be beyond that. And we, you know, who knows? One day we might be coding on 64-core chips. That doesn't seem unreasonable at all. And as we go towards that, the sort of the communication between those cores is going to get to be more and more of an issue. Not only that, but as we sort of discussed last time, the speed of CPUs has been getting faster exponentially. Everyone will have heard of Moore's law. Moore's law basically talks about that relationship where the number of the idea is meant to be that the number of transistors on a CPU basically double every 6 months, is it? 18. Yeah, that makes more sense. Otherwise it'd be a bit too fast, wouldn't it? But traditionally, the speeds for disks, whether it be SSDs have made a bit of difference because SSDs are much faster, but the speed for the buses to reach mass storage and the speed of reading from memory basically hasn't ever kept pace. So the gap between main memory and the amount of processing you can do in your core has been getting larger and larger and larger for many years. A lot of this has been compensated for by microprocessor engineers by basically making the CPU cores, using all those wonderful transistors they get from Moore's law, and basically making CPUs more and more complex, where they basically do a massive amount of work for you in basically trying to guess what it is you want to do and try and make that faster. Which is great because it means you can be lazy and they will do an amazingly good job at making your stuff fast. But the thing is, every now and then you do things in something slightly the wrong way, or you find yourself with an inner loop you need to optimize, and you find it's guessing wrong. And when it guesses wrong, everything just goes to hell. So a little what we're going to do is also just talk about how you can sort of make life a bit easier on that. The interesting thing is, as actually in doing my research for this sort of expanded version of my 15-minute talk from last time, that went 45 minutes, I've actually learnt a few new things as well. So some of those I'm going to share with you as well about some of the tricks that can help out with this stuff. So thinking about this sort of pyramid of access speeds, I suppose is the come on, wake up. Tell me that wasn't my battery going. No, I'll tell you what, I actually like whiteboards anyway. Let's go with whiteboards. Because the thing is, everything is up here. So I'm just going to go with it. Okay.
You're saying you've learned some new things?
Yeah, well, too, look, well, as I say, I was just sort of mentally remembering the order I wanted to talk about things. But look, as I say, I'll jump around as we go. Tell you what, just because you've stuck it in my head and it's in my head now anyway, one of the new things I learned about this is I now understand a bit better about... Okay, so one of the things we're going to be talking about the model of the CPU in general and the way CPUs deal with memory. So we'll just draw ourselves, because we'll... Oh, come on. Seriously?
It's like the world's
The
most
technology is
soft.
seriously found today. So much for using the whiteboard unit. Our model of the CPU for a modern one is basically you've got multiple cores, that each of the cores, this is going to be...
Let's see, we can break down something quick.
So what usually happens is, if you just say you've got a 4-core chip, each core is usually going to have its own L1 cache, and then there's possibly going to be a shared L2 cache for a pair of cores, and then possibly your whole chip is then going to have an L3 cache. Your sizes are going to basically be, your L1 is going to be your smallest, your L2 is going to be the biggest, your is going to be bigger than that, and L3 is going to be larger again. And basically, and speed goes inverse to that, so your L1's the fastest. Now, the way all this is managed is by the memory management unit on a CPU. And the memory management unit also manages virtual memory, which is something I didn't talk about last time, but I wanted to cover this time, because that's sort of going further down that stack. It's another thing about the whole memory model of the way a computer works. But if you guys do, if everyone in the room goes, I already know this stuff, let me know, we'll move on to the next part, because I don't want to cover anything that everyone already knows anyway, if that makes sense. Yeah, okay, so one of the things I learned when doing research, as they know, is basically the way the automatic prefetches on x86 chips work. x86 chips are basically the most complex of the bunch. Compared to and that's partly why they're such horrid power hogs, but also why they're kind of, you can kind of throw anything at them and they'll kind of eat it up. And like one of the things I started talking about last time, that we'll talk about this time, is basically having cache-friendly access, so that you're basically using as much of your cache bandwidth as you're pulling. So as you're pulling data in from main memory, using as much of that bandwidth as possible. x86 chips will actually watch your access for memory, and if there's a pattern that they can recognize, they will actually go, I see a pattern, and they will start prefetching the data for you automatically further on. And they basically have a startup phase where you'll get, so if you're in a tight loop, they'll run slow for the first couple until basically the memory management unit goes, aha, I've spotted a pattern here. And then they'll start prefetching, and of course the other thing is they will prefetch, they will also end up prefetching past the end of your loop, because they're going to be predicting that there's more loops than there actually are, if that makes sense. So, so of course, if you don't actually, if you can sort of run your own prefetching, which basically no one ever bothers to do because the CPU pretty much does it for you, it's just not worth the effort. You can sort of preempt that potentially, but it's one of those things where it's just going to keep going in the end. But one of the reasons that was interesting for me was I quite a while ago decided I wasn't going to try and do any live coding examples for this, because one thing I've found time and time again is that when you try and create synthetic examples of all of these memory issues that we're talking about, the synthetic examples just don't work because they run fast. You just do them and you go, hang on, that's meant to run really slow. I just wrote this horrid routine that's meant to be abusing them. And the reason is basically because whenever you try and do synthetic examples of bad behaviors thing, they're going to be really simple bits of code because you want everyone to understand what's going on. When you have a really simple little blob of code, the CPUs and their memory management units basically can figure out what the patterns are in your code and go, oh, no worries, I'll just fix that for you, is basically what happens. And that's the reason all those synthetic examples I always try and come up for this kind of thing don't work, because they're small enough that the memory management unit can just go, I see what you're doing there, and we'll just basically start pulling in data before you need it and do latency hiding, which is great, but where a lot of problems hit is when you get into large-scale programs where you're sort of hitting stuff all over the place and you lack those predictable patterns. Okay, I've kind of gotten ahead of us here. Let's go back. So, so we'll start with just talking about memory versus cache. Now I started saying, so memory, you often think about it as being byte, 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 and you've got lots of bytes. The thing is, any CPU architecture, when you come to a new CPU, beyond learning, whether it's 64-bit or 32-bit, and whether it's big endian or little endian, the other thing you should really find out about any new CPU you want to work on is how big is a cache line. basically, for anyone who doesn't know, a cache line is the unit of measurement, basically the basic unit that a memory management unit on a CPU will work with. So these days, if you're on like a lot of the mobile ARM chips, most of them have a 32-byte cache coherency line. On a 64-bit CPU, you're probably going to be looking at x86 chip. You're going to be looking at probably a 64-bit cache line. And if you're any of the current gen, I guess you'd call them, consoles, so PS3 or Xbox 360, they have really big cache lines, 128 bytes for them. So what that means is, if you have a structure and you structure your data, so let's say you've got all this memory here, and then you just want to get this little block of data there. When you go to access that, if this stuff isn't already in your cache, it won't just pull in that single byte. It is going to pull in the entire cache line around it. So that's going to be either 32 or 64 bytes. If you have a structure that happens to be, so for instance, let's say you have a 64-byte cache line size. If you write your C structure and all your data, just every time you add a new field onto your structure, it just adds more memory onto the size of the structure. If your structure happens to be 65 bytes, then you're going to have to pull in 2 cache lines, which is basic, so 128 bytes you're going to be pulling in. So you can, in a sense, you can start to think about the communication between the CPU and main memory as being a lot like communication between computers over the network. I reckon that's a really good way to think about it, and a really good way to start thinking about structuring code. Because really, with the way CPUs get faster and with the amount of time it takes to communicate between chips gets longer, that becomes, you know, the relationships of old-fashioned servers compared to your CPU speed becomes more and more like that. So last time I remember I mentioned, and I'll try and cover a bit this time as well, that you can even start treating the communication between chips a lot like you treat network communication between computers. And you can sort of treat, if you remember that picture I did have up there for a moment, you can almost start to think about your L1 or L2 cache as being like the memory that's local to your computer, and you know, for that core. And you know, you can actually communicate back and forth between cores without going via main memory. And you almost treat main memory like a great big database server off in the cloud, if that makes sense. Okay, so each chip usually just has its own L1 cache. If you're using what's called hyperthreading, what that often does is, the way hyperthreading works, how many people know how hyperthreading works? Okay, cool. I need to start throwing a few of these in, because this is where I'm just checking whether I'm just talking about stuff you guys already know, or if I'm just hashing over stuff you know. So the gist of what hyperthreading does is it runs 2 threads on 1 core. And they end up sharing an L1 cache. And obviously, if you're sharing an L1 cache, you're also sharing everything further down the cache line as well. What happens is, so I mentioned your memory management unit is pulling your data in blocks of cache line size for anything you want to access. Every now and then, you're going to run out of work to do on your core. When you run out of work to do on your core, it basically, okay, so x86 chips will actually do look ahead, where they'll actually start looking further down the instruction pipeline and go, is there anything I can do with memory I've already got? And it'll actually, that's so, when you've heard about, you know, in-order and out-of-order chips, that's the way an out-of-order chip works. It goes, okay, hang on, I've got this work I need to do that I don't have the memory for, but there's something I know I'm going to be asked to do in a couple of instructions' time, and I've already got the memory I need for that. So it will do that first, while it's waiting for the previous thing you asked to do. So that's basically between in-order and out-of-order chips. But sooner or later, particularly if you're doing this kind of thing, where you're pulling in way too much memory bandwidth for how much data you're actually operating with, you're going to end up basically stalling the pipeline, where it's going to go, I'm out of work to do, I don't have any more data. In the case of hyperthreading, what it does is, in that point it goes, there's nothing more I can do, so it switches threads, and it goes across to the other thread, and it'll basically work on that thread and go, right, what have I got data to work on? It'll work on any data it's got. And as soon as it gets to the point where it goes, there's nothing more I can do, I'm out of data, of course, sent off all its requests for the data it wants to work on. So all those requests are in the memory pipeline, because your memory pipeline, of course, gives you latency, and it switches back to the other thread. The hope being that all the memory requests that the other thread was waiting on will have had, another 50 cycles, hopefully, in the other thread to sort of get some of that memory back in, that they'll have more work to do again by now. So that's basically the gist of what hyperthreading is. By running two threads on the one core, that's how it's latency hiding. It sort of swaps back and forth depending on who's got memory available at any given time. So
it doesn't work for everything. I've seen a lot of those disabled for performance.
Yeah, well, the thing is, see, it's great if you've got really stally code. It's this kind of thing where you can basically take two stally threads, stick them on the same chip, and all of a sudden you magically get double speed. However, if your code, wicked. So basically, if you've got really stally code, and then you as I said, you stick two hyperthreading threads on one core. Hey presto, you just doubled your speed.
By filling in the latency.
Effectively by doing this. However, if you have a really tightly optimized inner loop that's making full use of your cache, then hyperthreading is all it's going to do is just cost you every time you do a context switch. Yeah, exactly. Well, yeah, exactly. It's going to you're dead right. It's going to halve your cache size because both threads have to share a cache, whereas if they're on separate cores, they get their own L1 cache. But not only that, but every time, of course, it swaps between threads, it's got to do work to swap. I suspect. Okay. Again, the caveat for everything I'm saying is I am not a microprocessor engineer. A lot of what I'm going to be telling you here is if you ever want to go to apply this, do go and Google it first. And when in doubt, profile. You can't take all of these these issues. There's so many interactions in the way modern CPUs work. You can. These are good general rules for how you design stuff, but you always need to test your assumptions by actually getting into a profiler. When you're not
very difficult to reason about how threads are going to interact as well, isn't it?
Yeah. What this is. You can. Well, threads absolutely. Yeah, like the way two threads will interact in terms of the way they might abuse your memory pipelines for getting into your memory. What this is probably more useful for is when stuff goes slow and you get into the profiler, you can understand why it's going slow and what you might be able to fiddle with to make it go faster. And you'll hit dead ends, but the thing is there are good general design principles here though, that if you work this way in general. She's even got, what's the time?
12:50.
12:50, right. That if you work this way, what I found is when you apply a lot of data-oriented design principles, I actually haven't needed to get the profiler out really anymore. Mainly because if you sort of structure your code in a cache-friendly way, pretty much the GPU always ends up limiting you. So it's one of those things where you don't end up having to do all the super hardcore CPU optimizations anymore, simply because there's no point optimizing the fast path. It only ever makes sense to optimize the slow path that's bottlenecked. And if you have fairly cache-friendly CPU code, I find it all just ends up running that fast that you pretty much always end up stalled by the GPU. It's actually, you're saying, hey, we should almost do updates at the start of the group. One thing I've noticed is the last couple of mobile phones, this is in the news, that have been announced, I've noticed the last couple of iPhones, for instance, have almost doubled their CPU speed, every new model. The latest iPhone has only bumped it by like 30%, but what they've done is they've stuck a much beefier GPU on it, which I suspect is probably because they've realised that there's probably as much CPU grunt as most well-written apps can exploit anyway. But if you want to for anything that needs the kind of power that a modern latest gen iPhone or Android phone can crank out, what they probably want is more GPU power, and I reckon that most games on mobile phones are probably getting, the optimized ones are going to be GPU limited, not CPU limited. Okay, so so if you go to jump back to where we were, so you've got your memory, your structure, and if you want to pick out that byte, you end up having to pull in the whole cache line. So what it does is it basically is, I want that, and it basically goes and asks the cache for it. If it's not in the cache, the L1 cache, you have what's called a cache miss, and you end up, so basically L1 cache goes and asks the L2 cache for it. If the L2, if you have and so on through all levels of cache you've got, on something like a mobile chip you'll have 2 levels, servers might have 3 levels. It's very rare these days to see a 4-level cache. I personally have never seen a 4-level cache. If you miss, so whatever your bottom level is, if you miss your last level of cache, in the literature, you'll see that referred to as an LL, last level cache miss. Whenever you have a last level cache miss, that basically means you have to go to main memory. That basically means, if you think of it in terms of an actual computer, it means the chip is talking across the wires, effectively, to other chips, the memory chips, instead of staying on the silicon inside the core, which is where all your caches live. Obviously, it's much slower to go to main memory. One of the things I was going to show that I had on the laptop was, has anyone seen it was a Google program, and now I can't remember his name because it was in my notes. The numbers every programmer should know.
Oh, the relative latency stuff.
Yeah. So it's all your. So basically, so remember that we had the pyramid. To give you a gist of what those times are now, the times that were shown in that talk, if you want to Google them, are out of date in the sense that they're aimed at server programmers really, and they're a couple of years out of date. However, a server from 5 years ago is actually kind of getting close to where a mobile phone CPU is getting these days. So oddly enough, I noticed that the numbers are actually still pretty good and pretty relevant. So the gist is, to hit L1 cache, as opposed to something being in a register, you're basically talking about half a nanosecond. It's as good as free. Basically, the only cost compared to something being a register is you basically have to actually run the load instruction to actually get it from the cache into a register, but that's pretty much the only cost for an L1 cache. L1 cache is almost not worth worrying about, if that makes sense. L1 caches these days seem to run about 16 to 32K, and there's usually a separate cache for data that's used by your code and instructions. I cache. So you've got your I cache and your D cache. Second level cache is usually unified. Your cost to hit second level cache, probably around, I think it was 40 milliseconds, I'm going from memory. L3 cache, I believe is...
Nanoseconds or milliseconds?
Sorry?
Nanoseconds?
Yeah, nanoseconds, yeah.
Okay.
Did I say milliseconds? If you hit 30 or 40 milliseconds for L2 cache, you would be in so much trouble. Everything I'm saying is meant to be in nanoseconds. I think it's about 30 or 40. I think once you go to L3 cache, you're looking at about... Okay, sorry, back that up. It's not 30 or 40 nanoseconds for L2 cache. I believe it's 30 or 40 cycles. L3 cache, you're talking about 100 cycles, I believe, if you have an L3 cache. A lot of chips won't have an L3 cache. When you want to go to main RAM, depending on the architecture you're dealing with, you're talking anywhere between 100 and 400 cycles. I can't remember what the hell that is in nanoseconds. However, then you've also got, okay, so once you go beyond that, you're starting to talk about the amount of time that it takes you to say, so that's your time to hit main RAM basically. Once you go beyond main RAM, you start getting to, say, virtual memory, where you might have to swap a page in from the hard drive or something like that. If your game is well written, you should never ever have to actually swap a virtual memory page. But if you do, you're basically talking a hard drive seek, and then of course the actual bandwidth time to actually then read that in. You've also got network latency if you're communicating over a network. Oddly enough, network latency these days can often be less than the latency for seeking a hard drive. You can actually send data between two CPUs over. A CPU on the other side of the world can be faster than getting stuff on your local hard drive.
Is that because more stuff is offloaded onto the network controller, independently, separately?
That's more just general latency. It's just that modern CPUs are fast, and the seek on particularly on a mechanical hard drive. Not SSDs are different. This is the reason there's a move towards SSDs. Mechanical hard drives are limited by physics in a sense. They've actually got to physically move an arm to seek to a location. If you're lucky, the arm might already be there. Then you're also limited by how fast the disk spins. And of course, this has all been improved by the density on disks is increased, which means that the magnetic head moving across the disk can pull in more data per spin and all that kind of thing. But things like seek times and RPMs, physics says you can't realistically spin a hard drive inside your mobile phone at 20,000 RPM, or the thing's just going to explode in your hand.
That's why defragmentation works in the first place, isn't it? Due to the fact that you've got to get every data close to the central ring as possible and glue them together.
Yeah. So you don't have, because we've got different spots on the disk. Your arm has to seek different distances. We've got a couple of old school games programmers in the room who've probably, when writing games for CDs, particularly on the older ones, like the double speed PlayStations, that kind of thing, CDs, where we would spend quite a bit of time arranging data on the CDs, so that any given level or that kind of thing, all of the data was in one spot on one ring on the CD, basically. So because if you had to seek your disk to, say, for instance, go get your music, and your music was a long way away, it could just kill your performance. Because the PlayStation 1 only had 2 megabytes of RAM, which is the L2 cache on my CPU at home is 6 megabytes. So it's 3 times the size of the main RAM, which was way slower on the PlayStation 1. So that's just you just couldn't fit our level in memory back in those days. You had to stream, if it was any size, you had to stream it off the disk. So you were paying for the physical cost of seeking your head around, unless you got your data all lined up, all your ducks in a row, so to speak. I'm getting off track again. This is, so as I said, disorganized. Okay, so where was I up to?
Pyramid.
L1K. So basically the gist is your cache lines in memory are all lined up one after the other, and they're all going to be in these nice 64 byte, 32 byte, whatever your cache line size is. They're all these different blocks. So if your structure is the wrong size for it, and then you build an array of them, you basically have this weird arrangement where you're going to be hitting more cache lines than you need to. You're going to be hitting random ones, and the pattern might even be hard to predict. This kind of thing here, where if you end up trying to iterate over an array and you just want to hit one value, this is the stuff that the prefetching has gotten really good at. However, even though the prefetching is going to hide your latency for you and it's going to get all that data for you before you need it, you're still pulling all of this data in from main memory. So if you think of this as being the same as a network, which is the way I want sort of people to start thinking about it, you're having to pay to send all of this across the network, so to speak, as opposed to only pulling across these bytes, which is the impression you'd get from just sort of the way the C language works. So it's good to start actually thinking about your data in terms of these blocks. What I didn't talk about last time is I didn't get to virtual memory, which is part of the larger structure. Back in the days of consoles and a lot of the stuff we worked on, you pretty much never ran virtual memory because, so I talked about the MMU before, which is the memory management unit. This is some of the stuff I know a bit better now than I used to before doing this. I did know this stuff, but I now get a bit more of the gist of it. Does everyone know, who knows what the translation look-aside buffer is? Right. We've got some little bits. So you got your memory, so your memory management unit isn't only pulling all your data in from main memory, it also handles virtual memory for you. How many people think they know how virtual memory works? Or think they know how virtual memory works?
Or virtual addressing at the moment.
Virtual addressing, yeah. So one of the things, so instead of thinking about memories, as I say, this big linear block, the other thing is, so you've got your L1 cache line size, your L2 cache line size are about the same size. You can just store a lot more of them in the cache. So you've got a larger amount of memory you can store there, but it's still working, generally speaking, in the same coherency line size. when you get down to the operating system level, the operating system when you run a process, and pretty much these days, if you're running on a mobile phone or a PC, or I suspect the new generation consoles are probably going to be running heavyweight operating systems as opposed to lightweight ones we've seen in previous generations, mainly because they're running on x86 chips now, and x86 chips have all this built in. You also have, the operating system works with pages of memory. On a 32-bit CPU, you'll often see a 4K page size. And on a on say Linux in a 64-bit chip, you'll probably see a 16K page size. So the way when you ask the operating system for memory, you do that by calling malloc. This is the same thing of like where I'm saying if you just allocate this block, you think you're just asking the operating system for a block of this size, right? That's not how it actually works at all. What actually happens is it asks every time you get memory from the operating system, you have to do a kernel switch. Now, let's not go into kernel switches. Let's just say that kernel code, jumping into kernel code, as opposed to running your own code that's local to your process, is expensive. So you don't want to do that. So what the C runtime, I talked about how a lot of these patterns and the way this model works comes from the C and C++ runtime and the way these sort of models work. It basically will ask for a page from the operating system. So that's going to be either 4K, 16K, whatever your page size is. It's going to get a whole page from the operating system. The operating system has no idea what you're doing with the memory in the pages it's got. All it ever does is hand you a whole page at a time. And then what it does is it maps that page into your local address space for your process. This is the reason that a pointer from you can't pass pointers between programs running on a computer, because of course those pointers mean totally different things because they're running in different memory spaces. That's because the page table, it's called, there's a table the operating system uses that basically says for any given address location that's a page, for this given process, that's physically in RAM where that page of memory lives. Is this making sense? I had a picture for it. I'll just draw you the quick version. So here's actual main RAM. Main RAM gets broken up into pages. Each of these, so whatever your page is, we'll say 16K because I'm fairly familiar with 16K pages. Each of these is 16K. Then you've got the page table, and then what it does is it says, okay, so you've got process A and process B, and I say I would like to malloc a structure of this size, and it goes, I haven't got any memory. I need some memory put this in. So what it does is the C runtime says, please get me a page from the operating system. The operating system says, sure, okay, I'm going to make one entry that maps address OX something 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 to this location over here. I'm going to give you that page. So that page now belongs to that process and it lives there. Now the thing about virtual memory, of course, is the operating system can actually shuffle these around however it wants, and it can also, if it wants, page them out to the disk if it starts running out of memory. So basically A might have a bunch of pages and they can be anywhere. And B also has a bunch of pages, and again, sorry, sorry, was there
I was going to say, wouldn't each process have its own page table, or is it?
Yes, but like there's sort of like there's the page table basically holds the lookups for all of the. Well, look, I don't know how I haven't looked into the way Windows. Obviously, you can't look at the way Windows does it. It's closed source. I actually haven't been to Linux code to know whether it's like they keep them entirely separately or whether it's one thing. But one of the things is the page table isn't just a structure that's been invented by the operating system. It's actually can basically be read by the translation look-aside buffer. When you in the CPU,
so the CPU provides support for it. Yeah.
There's actually just like you've got your L1 cache, your L2 cache, your L3 cache. The translation look-aside buffer is basically buffering entries from the page table. So that means when you're, because here's the thing, if your process says, I would like to get this byte from this location in memory, it needs to know where, since you, in a virtual memory system, which pretty much everything these days is a virtual memory system, it needs to know where in real RAM that relates to. So it would, if it had to access the actual page table that's in main RAM, it would have to go, it would potentially have to go all the way to main memory, or it might just go L1 or L2 or L3 cache to get the page table entries for where to look that up from. So that means, so this is actually one of the catches with the way this works, is if you go to get this bit of memory and it's not in your, and you haven't accessed it in quite a while, it's not necessarily, the worst case scenario is not just a last level cache miss. It's actually, you know, okay, the worst case scenario is it has to page it in from disk because you haven't accessed it that long ago.
A page full.
Yeah, that's page. But it can simply be that it doesn't know, it doesn't have in its limited size translation look-aside buffer the location of the page. And it's not in any of the caches. So you can actually have a last level cache miss from the translation look-aside buffer that's just trying to look your address up. It's got to go all the way to main memory to get the location from the page table. That's got to come back to the CPU, then it can say, okay, now I know where the actual memory I want is. And if that memory isn't in memory either, you might have to do another round trip to main memory just to look up one address.
So basically the CPU is translating your virtual addresses using the look-aside buffer. But if it doesn't necessarily have everything in there, it might have to go out to memory to the page table.
Yes, you can. I can't remember what it's called. You can have a look-aside buffer miss basically, and if you have a look-aside buffer miss, it's got to go get it from. Hopefully, it's going to be in one of your caches. Because I believe it won't ever use the L1 cache. I don't think. Don't quote me on that. It might be one of your caches, but if it's not, you could have to go to main RAM just to get the virtual address to actually look up where the memory is you want. Eek. And apparently, this is the reason no one ever used virtual memory on the PlayStation 2. The PlayStation 2 it had a memory management unit that was capable of doing virtual memory. It didn't have a translation look-aside buffer. So as soon as you turned on virtual memory on a PlayStation 2, you halved your memory bandwidth. Because every time you went to look up an address from main memory, I've heard, I can't vouch for this. Is anyone here who can, who's worked on PlayStation 2?
I didn't know even I had an MMU, so...
Yeah, no, but the thing is, the reason you probably don't know is because no one ever turned the damn thing on.
Because they did and said, oh, that's terrible.
Yeah, because it basically halved your memory bandwidth. Because you basically had to do 2 round trips any time you wanted to pull a cache line in the CPU. So this is the gist of the way virtual memory works. Now the thing is, so it pulls a page in, your process then has a whole page. Then has anyone ever written their own heap manager? Yep.
I mean, what manager?
Has anyone ever written their own memory manager? You will have written a memory manager.
Or like a DLL kind of thing, like a previous manager, that kind of thing.
Oh, it'd just be more like, here's a heap and written your own version of alloc and free that just works out of a pool, basically.
Yeah, many more times than I ever wanted to.
Sorry,
I wrote that.
you read that? If you've ever done that, basically the C runtime, it's just like another DLL. It pulls a bunch of code into your process. It goes and grabs a page, and then it'll carve off a bit, and it'll serve your allocation from that. So the thing is, it then basically, every time you do an allocation, it's just going to be taking allocations from the pages it's already got. And when it runs out, it's going to ask for another page. Now, one interesting thing that occurred to me when I was going through this, that hadn't really occurred to me at first, everyone knows that memory fragmentation is bad, but it had never really occurred to me before that you could theoretically fragment your use of your memory pages. Because if you, for instance, go, okay, allocate me a bunch of memory that I'm going to use temporarily while I'm doing a load, and then I'm going to load my actual data. Here's my actual data. Free these. It's still got to hang on to the whole. So if you're ever running like a long-running process that needs the same memory, and We're having to do that a lot these days because on mobile phones and stuff, a lot of the way they work now is they never really shut down the process because they want to be able to switch tasks really quickly. So they just leave the task running forever. So if you've effectively fragmented your page by, I presume it should be able to go back, it would be able to go back and reuse this memory next time you do
But
an
there's no
application.
keeping track of what's used.
VMs do a lot of work so that they allocate the same sized objects in the same, in effectively in arrays to
Yeah.
produce heap fragmentation. You talk about heap fragmentation.
Yeah, but the point being that
Just in one particular page, though, as well.
Yeah.
it's unlikely unless you depending on the process you do. But if you say, for instance, had a whole bunch of pages, and you happen to allocate lots of memory into them, then you freed a whole bunch of stuff, but you left say a couple of allocations in each of them.
Yeah.
In terms of the amount of, I'm not saying it's likely, but it had never occurred to me before this stuff that it was even a possibility. If that makes sense.
Mm.
And all this, and your process, your process can't release that memory back to the operating system to use for other stuff in a low memory situation because you've fragmented your use of pages. If that makes sense.
Yeah.
It would have to be a pretty particular circumstance
No, I
to
reckon-
actually pull it
I
off.
think it happens more
I
frequently
think it
than you
happens,
realise.
in fact, all the time.
Yes.
And there's special code to compact.
Especially in VMs where you're dealing with stuff that allocates at this point in the stack or that point in the stack, where they're dealing with heap space instead of stack space.
Mm.
They do it all the time. They've spent the latest .NET 4 VM has some serious stuff in it to do with that sort of stuff.
Right.
It's scary.
See, the thing .NET being a managed language, I would not be surprised if .NET is able to actually relocate memory behind the scenes.
Yeah, you can.
Yeah, I would think it would.
I haven't hit that, but I do know they do a lot of work to try and keep the same size allocations, or this range of size allocations. This is this chunk of memory, so that they don't make big holes in large spaces and that sort of stuff.
And then reuse them.
Yeah, it's scary stuff.
Funny you should say that. That's exactly the way memory should be managed, and that's part of what we're about to go into.
Funny that.
Because one of these, so you can sort of see how operating in terms of your cache line size means effectively, you think of arrays, and your arrays just end up being an array of structures. There is a natural array size, if that makes sense, in the way you operate with memory, and it's multiples of cache lines, basically. The thing is, cache lines will always fit evenly into a memory page. So for instance, if you've got a 4K memory page, I have to do the math in my head because I have it written down. A 4K memory page, and you've got a 64 byte cache line. I believe that's 64. The 64 into 4K goes 64 times. I believe it's 64 cache lines. Okay, now so one of the things is when you're dealing with cache lines, the other thing is it's also, you also do want to be dealing with your memory in a fairly linear way, because you've got the prefetcher is going to be predicting where the memory is you want to get. If you're using something like, say, a linked list just from random mallocs that you've mallocked and they're all over memory, you're basically going to be doing, firstly, if you look at this and you think about all that latency hiding I was talking about, you're going to be having, you're going to be doing what are called dependent lookups, where it's going to want to go, okay, work on this, and now I want to work on the next thing. And if it's a linked list, you have to use a pointer, right? So that means you've already got to have that pointer in memory before you can even look up the location of the next one. It's a bit like when you have a TLB mess. It can't latency hide if the next lookup is dependent, if that makes sense.
It's the cost of indirection, basically, isn't it?
Mm. Whereas if you're working in
It's like saying with a virtual function lookup in C++.
Oddly though, with your linked list example, a lot of the time the linked lists get built in one hit. So you have a pattern of access for the nodes, and that's when the pattern from your x86 MMU will be the cache lookup.
Depends.
Yeah.
Because
It always does.
it
always depends.
Well, here's the thing. Because the pattern matching, it's not doing Bayesian heuristics.
No.
This sucker
It's a stride.
it's
size.
It's built into silicon, so it's simple. Apparently, the old ones would basically figure out when if basically they work off cache misses. So if you went miss, it would go, oh, hang on, I better load that one now. I've sort of illustrated an example here where they're not in even intervals of occasions. I believe the modern ones can predict that. If it's a case of I'm going to do this one, then this one, then this one, then this one, or even if I'm going to go here, then do 4 or 5, which is the way tree structures will often work. Then I'm going to jump back to this guy because I'm now on the left side of my branch, which is going to jump me over here, and I'm going to do 6. You can actually conceive of a situation where the prefetcher is actually going to make your life much, much worse. Because what you might do is you might go to this bit where you're going to do a bit and you're going to go fetch, fetch, fetch. At which point, these ones have all missed. The prefetcher is going to go, aha, you want a whole bunch of memory up ahead, and it's going to go fetch, 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 and you only actually do one more, then you jump back over here. And you might have just blown a bunch more bandwidth to go out this way, and then you jump back here, and that's another miss, and then you're going to jump out there, and it can all, could all just go to hell. So so that doesn't mean don't use tree structures. It just means that what it means is don't use linked lists. Linked lists suck. If you're going to use a linked list, it's going to want to be small, and it's going to want to be something you don't touch a lot. Linked lists on modern CPUs just suck. Just don't.
But as with all performance-related stuff, if you don't need the performance, it doesn't matter.
Yeah, well, that's why I say if it's that's why I say for the big things. If something's big is when you need performance. Something you do a lot of.
And I got this feeling as well that if you're going to go and sort of practice this data-oriented design and try and optimise your data aggressively for the particular CPU, that if you do it naively and you don't actually have a lot of experience doing it, you're probably going to make things worse for yourself. Especially because modern CPUs will do a lot of this for you, right? And there's no reason to think that you have to know what it's going to do on a lot of different CPUs as well, I think.
Well, that's the thing. Well, so hopefully I'm giving enough information to be dangerous.
This is the generic explanation.
But this is why I did say at the start, Google it. Basically, this is not enough information to work with by itself. This is enough information that this is one of those things. My approach to this, in a sense, is I'm not going to be able to dump enough memory on you, knowledge on you to be able to just go and write this, if that makes sense, straight away. But these days, Google has all the information in the whole world at your fingertips all the time. The problem is when you don't know what to Google. What I'm trying to do here is give you guys a primer, so it's a case of when you go to do this, and when it all goes horribly wrong, as it inevitably will, you're going to know what to Google for to fix it. To learn about what the particular aspect is or the thing it is that you're dealing with at the time. There are general things you can do that you can pretty much guarantee are going to be fast in any modern architecture. And we're starting to get at the guts of it, but where are we for time?
Yeah, 20 past 1?
20 past.
It's still daylight.
So I think we can start for about 20 minutes in, so I'm at about an hour in now. Okay, just to jump out a bit, I actually like it when people interrupt and we get in the discussion a bit and stuff. We're starting to talk about here the way you can sort of start to treat data as basically arrays, and you can start thinking about cache size. How many people have done GPU shaders or any GPU programming? If as soon as you start doing shaders and you start doing modern programmable pipelines, I reckon that's about the best example of when I was later on going to start to talk at that stage about data-oriented design. I think the best description of it, you can go away and read about it, Google about it. I don't need to teach you all about data-oriented design now. I reckon most of the principles of what data-oriented design is, you end up designing your CPU code the same way shaders work, basically. If you start to think about the fact that you're working with these blocks, if that makes sense, and the things, and you try and make your and a lot of this stuff all applies to GPUs as well. This is the reason that when you're writing your your vertex buffers, for instance. You want your vertex buffers to be a nice power of 2 sizes. You want to pack these because you've got the same kind of thing. It's not necessarily such a big deal because you're going to be sequentially dealing with it, if that makes sense. This can matter more when you've got random access going on, if that makes sense, when you've got holes, if that makes sense, and you're pulling in too much. But if you're using, the gist of this stuff here is that if you're going to bother to touch a byte in this structure, you may as well touch all the others because you're paying for them anyway, if that makes sense. That's the general idea. And the other thing is, you don't want to write your code and your passes in such a way that a good rule of thumb for games is you only want to touch any given cache line once, maybe twice per frame, if you can avoid it. So, as you say, now the important thing to point out here is this stuff is, like I said, when you start to talk about that stuff, last time I did this, I talked a lot more about the multi-threading aspects of the cache line stuff. And I was talking about that stuff. I think is actually, we'll hit that in a minute, and we'll do another recap of what we did in the last one about the way you can, communication between cores works with your cache lines. When you're getting into the sort of the really hardcore cache stuff, yeah, don't worry about it too much, because most of your code, 90% of your code, it just does not matter because the CPU is going to do all the hard work for you. This is the stuff that matters for the big data systems. We're talking particle systems, rendering systems, physics engines, any, well, that's physics as well.
Anything that where there's a large amount of data potentially limited by the memory bandwidth.
Yeah. But even beyond that, now Unity, I've noticed, seems to have a slightly data-oriented-ish kind of structure, because you'll notice that they've got their whole thing of where you've got. I've learned a little more about Unity recently than I used to know. So you've got game objects, and then it adds all your components to it. I suspect that the way they work under the hood is that when for each of your components, if they're doing it right, we'll say, all of the components you add to a game object under the hood are definitely not stored in one big blob in one spot in memory. If they are, they're doing it wrong.
All the components are like arrays, pools of components.
So when you have your transforms you've added to this game object, and your transforms that are added to this object, and your transforms added to that object, I would think that what it's doing is each of those objects is actually storing not a pointer even, but I would say an index into a big array of transforms that they can possibly run across and do a lot of stuff on all at once, if that makes sense. So they probably, the way you, transforms might not be a great example because they're a bit complex in the way you might deal with them. Sound effects. And so what you can do is, you can basically, you sort of almost then want to do, because this is, we're talking about decache here, but the other thing is, the other part of data-oriented design is it's also can be, if you think about doing stuff a bit like shaders that run across blocks of memory, that's also really friendly to the instruction cache, because your level 2 cache, you have to share between the instruction and data, and you've probably only got a 16K or 32K of instruction cache. So you can be thrashing your cache for instructions as well if you're doing really big blobby code. If you do stuff that, if your code, is small and you're running the same thing in a tight loop, so you do this thing in a tight loop and hit all these bits of data that are all the same, and they're all in a nice, and you haven't allocated them here and there all over memory, and you're using pointers to get to them in a completely unpredictable pattern. If instead of using pointers to get to these blocks that you've just stuck all over memory as you happen to get to them, you put them all in a nice read array, so you use indexes into the array to access them. And then in terms of processing, you come along and you go, right, it's the time to deal with this particular type of object. And we have a particular way of dealing with them. Now, they're not like C++ structures where you do, you've got class derivation, so they can all be different sizes. They're all this block of size, and you go, right, boom, 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 boom. It's friendly on the I cache, it's friendly on the D cache, and it will just go through. So this is just system stuff.
Eventually you get into Unity's C++ plugins. That would probably, their API for C++ might tell you more about how that's structured. Because I know for a fact from C# you can't get into their rendering pipeline at all.
Right.
It's just completely closed off.
I thought you could with Pro.
No.
No.
You can render stuff, and you've got some basic access to GL functions to render stuff,
Yeah.
but that's all off to the side. You can't get into change anything to do with the way the meshes are rendered, culling, anything like that.
How about state sorting? How do you sort of, we're getting off topic again. But
Yeah, it's just all automatic. You can't.
So it calls you when it's ready for your state, is it?
You just configure materials, and you don't get to say.
Oh, so you can't make your own GL calls to configure anything. Or anything.
It's like you pretty much don't override the rendering pipeline at all. You can do bits and pieces. But
they've got a lot of smart people there. You want to hope they're doing it right. Doesn't mean they're necessarily. But
yeah, I was just thinking. I don't know if you can give them that much credit, but
because one of the things
the way they've closed it off, they've given themselves a bit of leeway there. I think.
Yeah. And, well, here's the thing. You know, I'm a bit anti-Unity, and the rendering engine and it all being closed off like that is one of my major things. And some of this is possibly said. Look, I've looked at Unity and it's well designed on the outside, but the thing is, the same problem that UDK has. They were both designed to be PC engines, and they were both designed circa 5+ years ago, so older hardware as well. And I'm betting that first time through, I'm pretty certain almost for a fact that Unity on its first pass wasn't designed for programmable shader pipelines. It was designed for fixed function.
Yeah.
And they.
Oh, there's very many signs in Unity that becoming popular took them completely by surprise. Like they hadn't designed an engine that was going to be, that popular.
So they've had to sort of back. And the other thing is, I'll bet that the first version wouldn't have been multi-threaded either. I'm betting the first version would have been single-threaded because just the era.
Well, you can't do much in threads in Unity. I mean, we have a couple of threads running for like the web server and stuff like that. But you can't call any Unity APIs from a separate thread. It'll just throw an exception on you.
Right.
So. But I mean, that's the way APIs tend to be going. Right?
A lot of this stuff is all about scalability. This approach is about how you build stuff that goes to big, if that makes sense. Yeah. So here's the thing about pages. I want to get off this stuff actually pretty soon because otherwise I'm going to run out of time to hit the other aspect I want to hit, which is the multi-core stuff that we covered more of last time, and then we'll leave it at that. I think you're paying for if you're on a virtual memory system, you're paying for the overhead of it running this way anyway, and most of the overhead is just being handled by a dedicated bit of silicon, so it's basically free. If you're paying for it anyway, hell, we're games programmers, we hack on stuff. If you're not using Unity, and I know everyone's using Unity for everything, and you can get into this stuff yourself. If you start to think about that, now as you can see, it's the C runtime that goes to get the pages from the operating system and say, please give me a page. Now, I need to jump back 2 steps. So, if you're going to start treating stuff you start treating your memory, instead of it being like, here's 0, there's 1,000,000, and all the memory is just a big line like that of bytes. You start to think of it instead about, okay, we've got these discrete blocks of cache lines. Within that, we talked last time about, SSE vectors as well have to load on 16-byte per line, which you'll fit either 2 or 4 of those, or 8 in the case of a PowerPC console, into a cache line. So they all divide evenly. So you've got your bytes. Your bytes line up evenly into your ints when your ints are aligned, 4 bytes at a time. They line up into your 16-byte SSE loadable vectors. They then line up evenly into your cache lines. Your cache lines then line up evenly into your pages, if that makes sense. So if you're going to start to think about things as treating these as these sort of array of usable blocks, and you only ever want to hit any given block at a time, and you've got pages, 64-byte pointers are really big now that we're on 64-bit architectures. 8 bytes is a lot of memory to get to something else. A lot of times when you start dealing with these things like arrays, if you start using indexes instead, you'll find that 65,000 is a hell of a lot of objects. If you can get away with 65,000 objects and you start using indexes instead of pointers, you can use a quarter the size to store your index. Now, so for instance, let's say we've got a 64-byte cache line. You've got this grin like you've heard this all before.
Oh, I've been through this in a VM land where it hit 64 byte space and the memory footprint of the program jumped from 400 megabyte to 900 megabytes.
As soon as you go to the big...
And I ended up converting from a list of classes to arrays, which is ugly in C# because C# expressivity vanishes the minute you can't deal with classes. You have to start dealing with arrays. You have to start handling extra indexes all over the place. It just gets really ugly. But it dropped the footprint down insanely.
It's the funny thing, as soon as you get big or high performance in C++ or C# or whatever, in these object-oriented languages, you hit these exact same problems. It's really funny. So starting to treat big chunks of your system, anytime where it's big, more like shaders, if that makes sense, where you sort of the other thing about treating them like shaders is, we're going to talk about multi-threading stuff in a bit. The nice thing about that is that they make these really nice discrete blocks that you can just send off to another core to worry about, and you can almost treat the other core a bit like a GPU. And that's where all the stuff where we talked last time, and we'll get to it in a sec, hopefully, the communication stuff is almost treating it like network communication when you're going between your cores. You can sort of almost treat that as the same as you would your bus going to your GPU. And the interesting thing being, when you get to say a PS4 or an Xbox 360, the new chips, they've stuck them together on the same die. They've actually made them cache coherent between on the PS4. The PS4 is cache coherent between the CPU and the GPU. So you can actually have cache coherent traffic going where you can, so that means you can actually hand GPU compute jobs really easily back and forth between the CPU and the GPU and the PS4. I haven't touched the PS4, mind you, but this is from everything they've released about how they work. Okay, so indexes, really nice. All of a sudden you quarter the amount of use of space it takes to tell you where something is. And the other thing is, just say you're using decide to use indexes into cache lines. It doesn't have to be cache lines, it could be in double cache lines or half cache lines, depending on what particular structures you want to store in this case. 65,000 times a 64-byte cache line. Oh, by the way, when you're choosing your structure size, if you need to run on multiple architectures, go with whatever, and you need to sort of pick a size, go with whatever the biggest size is, because if you go with the smaller size, on the big cache line architecture, you might be wasting half your bandwidth, if that makes sense, by having to pull in the whole cache line and only using half of it. Whereas if you use the whole cache line on the smaller architecture, all it means is you have to pull in 2 cache lines, but you're still using it all, if that makes sense. So it's not lowest common denominator, it's kind of highest common denominator, if that makes sense, when it comes to cache line size use. So 64 byte, so basically if you say 64K, so the amount you can store in a 16-bit pointer, times a 64-byte cache line, you get 4 megabytes. So you can basically address 4 megabytes worth of memory as an array. When you're using virtual memory pages, you can actually allocate virtual memory pages yourself from the operating system. On Linux, use mmap, for anyone who hasn't heard of it or used it before. And on Windows, you use a function called virtual. I have no idea what you use on iPhone or iOS or BSD, but it might be mmap. I wouldn't be surprised. They're very Unixy on most of the Apple stuff. Mmap looks like it's just for mapping files into memory, but that's the funny thing about it. When you first read, like, this is for files, I don't quite get it. Whereas virtual looks like it's for this on Windows. But when you look at it deeper, where it wants the file handle, basically you just tell it null, and what you actually get is the operating system maps a page for you. This is actually what the C runtime is doing under the hood. Now, as soon as you start allocating your own virtual memory pages from the system, a whole bunch of cool new tricks opened up to you as well. You can do stuff like, you can lock pages into memory so that they never page out to disk. You can flag a page and say, this page never goes to CPU, it never goes to disk, I always want to keep it in memory. You can also, if you ever want to generate your own code, most of us don't do that these days, you can flag a page as being executable. So if you ever need to execute, generate code, you have to allocate pages because you need to mark